The Dream Machines: How Deep Minds Set Out to Build a Mind. Demis Hassabis was 8 years old when he used chess tournament winnings to buy his first computer. Even then, something clicked in him that most kids his age couldn't articulate: the sense that machines might one day extend the reach of human thought beyond anything we could currently imagine. That intuition would quietly drive the next 3 decades of his life. He was an unusual child. By 6, he had already won the London Under-8 Chess Championship. By his early teens, he ranked among the top young players in the world. Chess seemed like his destiny, until a brutal moment at a tournament in Liechtenstein changed his thinking forever. Exhausted after 10 hours of play against a former Danish champion, young Demis made a catastrophic error. He resigned a game that was actually a draw. His opponent leapt to his feet, laughing, and demonstrated the saving move with a theatrical flourish. Demis felt sick, not just from the loss, but from a sudden, creeping realization. He looked around that enormous hall, filled with hundreds of gifted minds locked in silent concentration, and thought, is this really the best use of all this intelligence? What if those same brains could be pointed at cancer, or disease, or the deepest mysteries of how life works? He never quite looked at chess the same way again. The Secret Company. Years later, after studying computer science and neuroscience at Cambridge and completing a PhD, Hassabis co-founded a company with his longtime collaborator Shane Legg. They called it DeepMind, and its stated mission was almost comically ambitious: build the world's first artificial general intelligence, a machine that could learn to do anything a human mind could do. In academic circles at the time, saying you worked on AI was nearly an embarrassment. Serious scientists didn't dabble in science fiction. Hassabis and Legg felt like keepers of a secret no one else would take seriously, so they decided the right move was to stop asking for permission and start a company instead. Finding early investment was an adventure in itself. They pitched the idea of solving all of intelligence to rooms full of venture capitalists accustomed to asking about product roadmaps and quarterly revenue projections. The conversations did not always go smoothly. Eventually, the contrarian billionaire Peter Thiel, known for betting on ideas that the rest of Silicon Valley dismissed, became their first major backer, on the condition that they relocate from London to California. Hassabis pushed back. He wanted to stay in London, draw talent from Oxford, Cambridge, and University College London, and build something with patience and depth rather than the Silicon Valley habit of founding, failing, and pivoting every 12 months. AGI, he argued, was not a 12-month problem. In the end, they reached a compromise. DeepMind would remain in London. For the first 2 years, the company was invisible. No website. A secret office. Employees were asked to be vague about where they worked, and at least one job candidate texted their spouse the address before walking in, just in case it turned out to be a kidnapping. Games as a proving ground. The team made an early and deliberate decision. Games would be their laboratory. Not because anyone cared about winning games, but because games offered something uniquely valuable: a clean, measurable environment where an algorithm could try, fail, learn, and try again millions of times without human supervision. Their first major experiment combined 2 powerful but previously separate techniques, reinforcement learning and deep learning, into a single system. The idea was straightforward in principle: give the machine nothing but the pixels on a screen and a score, and let it figure out everything else on its own. They started with Pong. It didn't work. Weeks passed without progress. At one point, Hassabis and Legg quietly wondered whether they were simply wrong about the whole approach. And then, without warning, the system scored its first point. Then another. 3 months later, no human could beat it. They hadn't told it the rules. They hadn't explained the objective. They had simply let it play, rewarded it when the score went up, and watched it teach itself. Breakout followed. After a few hundred games, the system had discovered not just how to play competently, but had independently invented the optimal strategy, tunneling around the side wall to send the ball behind it. A trick no one had programmed, and one that genuinely surprised the researchers watching. The system then learned to play dozens of other Atari games from scratch, using the same algorithm, the same architecture, the same blank starting point. Nothing built in. Everything learned. It was, the team believed, the first faint glimpse of something that could honestly be called general. The Go moment. What came next was watched by the world. Go is a board game so ancient and so complex that the number of possible board positions exceeds the number of atoms in the observable universe. For decades, it had served as AI's great unconquered mountain. Chess had fallen to machines in 1997 when IBM's Deep Blue defeated Garry Kasparov, but Deep Blue was a brute force calculator, built to do one thing and nothing else. Go was different. Its depth was not computational but intuitive, strategic, almost aesthetic. Experts believed it would take another decade, maybe more, before any machine could challenge the world's best players. DeepMind disagreed. Their system, AlphaGo, was trained first on the recorded games of strong amateur players, learning to mimic human decision-making, and then set to play millions of games against itself, gradually surpassing everything it had ever seen. When it traveled to Seoul to face Lee Sedol, widely considered the finest player of his generation, the atmosphere was extraordinary. 1,000 spectators. Television coverage. The weight of something historic in the air. During the second game, AlphaGo played a move that left professional commentators stunned into silence. Move 37. Analysts estimated that a human player would have chosen that specific move roughly once in 10,000 games. It wasn't just unusual. It revealed a strategic understanding of Go that human players, in thousands of years of study, had apparently never encountered. Lee Sedol left the room to collect himself. AlphaGo won the match. In China, the government cut the live broadcast feed partway through the first game. The moment was being compared to Sputnik, not as a celebration, but as a wake-up call. The team went further. They built AlphaZero, which stripped out even the human game records. It started with no knowledge of any game whatsoever, not the rules, not the history, nothing, and within a single day of self-play, it had become stronger at chess than any program ever built. By dinner time, the mountain that mattered. But for Hassabis, games had always been a means to an end. The real goal was science. Ever since a conversation in his Cambridge dormitory, when a friend named Tim Stevens talked about protein folding with something close to religious intensity, the problem had lodged itself in Hassabis's mind and never left. Proteins are the molecular machinery of life. They are built from chains of amino acids that fold into precise three-dimensional shapes, and those shapes determine everything: how a cell functions, how disease progresses, how drugs might intervene. If you could look at a protein's amino acid sequence and predict its folded structure, you could potentially accelerate decades of biological research into years. You could design new medicines. You could understand diseases that have confounded scientists for generations. The problem had resisted solution for over 50 years. Thousands of researchers, enormous amounts of time, painstaking laboratory experiments that sometimes took years to resolve the structure of a single protein. Hassabis believed AI could crack it. Most people, he told, responded with polite skepticism. DeepMind entered a global biennial competition called CASP, the Protein Folding Olympics, and finished at the top of the rankings. But finishing first at a problem the world was collectively bad at wasn't the same as solving it. The predictions weren't yet accurate enough to be practically useful. The team knew it, and it stung. Hassabis regrouped. He assembled a dedicated strike team, brought in researchers with actual biology backgrounds, rewrote the data pipeline from scratch, and pushed hard on new ideas. Progress came slowly, then all at once. By the time the next CASP competition arrived, the world was locked down by a pandemic. Researchers worked from home, delivered groceries to elderly parents, watched their children count the days since lockdown began in handwritten journals. And in spare bedrooms and kitchen tables, they folded proteins at a rate that would have been unthinkable a year earlier, hundreds per second, where before it had taken days. When the results came in, one of the competition's senior organizers sent a short email. He called the performance really outstanding and noted that it exceeded all expectations, both relative to other teams and in terms of raw accuracy. The team read it aloud on a video call and then sat in silence for a moment. After half a century, the protein folding problem was solved. Opening the doors. The decision about what to do with this breakthrough was made quickly and with unusual generosity. Rather than building a subscription service or selling access or licensing the technology commercially, DeepMind chose to release it to the world for free. Within months, they had predicted the structures of 200 million proteins, essentially every known protein in existence, and uploaded the entire database for any scientist anywhere to use without charge. The day the database went live, the concurrent user count climbed past 100,000 within hours. Researchers in Japan, biologists in South Africa, chemists in university labs who had spent years waiting for a single structure that they now had in seconds. For many on the team, it was the moment that made everything feel real. Not the competition win, not the internal celebration, but watching a map of the world light up as scientists everywhere dove in. What comes next? Demis Hassabis is careful and thoughtful when he speaks about what artificial general intelligence will mean when it arrives, and he believes it will arrive. He worries openly that the technology is developing faster than the institutions meant to govern it. He has spoken about the need for global coordination, for serious ethical frameworks, for a culture in science and technology that interrogates its own power rather than celebrating it uncritically. He draws a pointed contrast with the Manhattan Project, where the excitement of achieving something unprecedented outpaced the moral reckoning that should have accompanied it. He doesn't want to repeat that mistake. But he is also, at his core, a person who has believed for most of his life that intelligence, real, general, flexible intelligence, is the most powerful tool humanity has ever had access to, and that amplifying it artificially could be the most consequential thing our species ever does. Bigger than electricity. Bigger than the internet. He was 8 years old when chess winnings bought him his first computer. He has been building toward this moment ever since. The game, as he might say, is just getting started.